So this time we're going to take a look at a slightly more difficult problem. This one's similar to one from the homework, but this one's going to be a full statics problem. So what I'd like to do is I'd like to hang a shelf. I'm going to have 2 wires to support that shelf, and the shelf is going to be 1 meter long. So this is 1 meter. I have 2 wires. I'm going to call this one wire B and this one wire A. I am hanging this shelf so that I can put a little knick-knack, a small snow globe or something like that, up on it, and I plan to have it slightly off-center so that I can add to the feng shui of the room. It needs to do something or some such with the energies and whatnot. I can't keep this joke going. I'm just going to give up. So I'm going to have a knick-knack here, and I'm going to have it 25 centimeters from wire B. I want to find out what the forces are going to be in these 2 wires so I know what type of wire to get. If I should use wet spaghetti noodles or old stamp roll paper like I did when hanging my camera from the ceiling, foolishly. Instead, I'd like to have a better idea of exactly what forces are involved. So I will tell you that the mass of our knick-knack is going to be 1.2 kilograms, and that the mass of our shelf is going to be equal to 0.5 kilograms. Okay. Okay, so ignore the ambient noises. What we're going to do first is use some of our new information. Use torques. Okay, so for this guy to be not moving, this is a statics problem. Static means not moving. And what we need to satisfy in order for something to not move is that the sum of forces on it have to be equal to 0. And the sum of torques also has to be equal to 0, where forces are in newtons and torques are in newton meters. Alright, so what I'm going to do is I need to find my sum of torques about a given point. It's usually a pivot point or something like that. In this case, because the thing isn't going to be moving, my sum of torques around all points actually has to be equal to 0, and we'll explore that once we get to the end. First, we'll solve this and see what happens if we did things a little bit differently. What I'm going to do is I'm going to choose my point wisely, because I do not know the force of tension in A, and I do not know the force of tension in B. That's what I want to find. So, since I have 2 unknowns, I'm going to use my sum of torques in a creative way to get rid of one of them so I can solve for the other. So I am going to set my pivot point right here, where B meets up with the shelf. Okay? So I'm going to do my sum of torques about that point. Okay? Well, first of all, I have the force of tension in wire B, but it's right there at my pivot point, so my lever arm is 0 meters. I'm also going to point out that of the forces we have involved here, we have tension in A and B, which are pointed upwards. We've also got the weight of the knick-knack pointed downwards, which will be little mg. I know that can be kind of hard to see, I apologize. And we will have the shelf. Its weight acts at the center of the shelf, and its weight will be big M times G, the way that I've got these set up with my variables. Okay? Where big M is the mass of the shelf, and little m is the mass of the knick-knack. Okay, why I bring this up now is, if you take a close look, my angle for all of these forces is actually 90 degrees. So I'm going to skip over, to keep things a little bit simple, our sine theta, because in all cases it's going to go to 1, from theta being equal to 90 degrees in each of these. Okay? So, I would have a 1 here for the sine theta, but we're not going to bother with that too much. Okay, so this guy, that's going to be gotten rid of, because that's why I've set my pivot point there, the point that I'm taking all of these torques about. Okay, well, if I look at the force of tension in A, it's going to be applied at a distance of 1 meter. That's my lever arm. It's also at 90 degrees, so I'd have 1 over here, but I'm not going to worry about that. Now, to keep with convention, imagine if this was the only force working on it, it would make that shelf spin up like this, which would be in a clockwise direction. So I'm going to label that direction negative. Okay? The other forces that I have that are supplying torques, I've got gravity, or the weight, I should say, of the board itself, times its lever arm. It pulls on the center of the shelf, so I'm going to put 0.5. And in this case, if I look at it acting just by itself, it's going to make the shelf swing downward, which is counterclockwise, which is positive. Finally, I've got also downwards, so positive. I'm going to have little m times g times 0.25 meters, which is the 25 centimeters that I have it from where B is. Okay. If I start evaluating these, as a reminder, for statics, we need our sum of torques to be equal to 0, so I'm going to do 0 equals. 0 equals, that guy's just 0, so he's out of there. We've got minus force of tension in A times 1 meter, plus, I'm going to put 0.5 kilograms in there for the mass, and I'm going to use 9.81 as G. Remember, no negative. We're keeping track of direction in all of this ourselves, right? We haven't used negative 9.81 meters per second squared since projectile motion, and we never called it little g back then. We're just using the magnitude, because we've already taken care of direction. So we're going to take the mass times little g, which this is being hung on Earth, times our lever arm, and if I evaluated this correctly, that should come up to 2.4525 Newton meters. Okay? Plus, same thing here, I'm going to put in 1.2 kilograms for that, 9.81 meters per second squared, and 0.25 meters as my lever arm. And I end up with 2.943 Newton meters. Okay, well, the only thing I don't know is my force of tension in A. I can add it over to the other side and then divide by 1 meter across the board. And doing the math, I find that the force of tension in A is going to come up to 5.40 newtons. There, we're partway done. Cool. Now, the next thing that we want to double check, because if we want this thing to not be moving at all, we need to double check that our sum of forces equals 0. Well, I'm going to save us some time here because looking at the forces that we have involved, they're all either up or down, nothing left or right, so we don't have to bother with doing our sum of forces in the x direction. Now, if we had some going off at angles, or we had some forces that were going side to side, then we would need to do our sum of forces in the x and make certain that they come up equal to 0. But in this case, this is a nice simple one. We're going to have 0 equals our sum of forces, in this case, just in the y, because we know that the sum of forces in x is 0, because there aren't any in x. And I'll find that, well, I've got the force of tension in A, which is up, so that's positive, plus force of tension in B, that's up, so that's positive, minus the weight of the shelf, mg, and minus the weight of the knick-knack, which is little mg. Well, we found the force of tension in A, that's 5.40 newtons, plus force of tension in B, which is what we're looking for, minus mass times gravity, big M, times little g, for the shelf is going to come up to 4.905 newtons. Remember, we're doing sum of forces, so we don't include the lever arms. We're just doing the forces themselves. Minus, this guy should come up to 11.772 newtons. Pardon me. Remember, all of this is equal to 0 because of statics. And when I do all the math on this, I find that the tension in B comes up to 11.3 newtons. There. I've now applied the rules of statics, where my sum of forces equals 0 and my sum of torques equals 0, so it can't possibly be moving because that would require it to have a net force acting on it. And it also can't be spinning because, or it can't begin to spin, I should say, because that would require a net torque to be acting on it. So, the way we've got it set up, everything is good. Now the final thing that I'd like to do, now that we've got that, is point out something interesting that comes up from this. And I need to grab my eraser. I think I have some room back over here. I'm going to erase part of this so that I've got some room, and I'm going to try over here to double check something. So, I told you at the beginning that we could set our point for our sum of torques anywhere we'd like. I arbitrarily decided to get rid of B. Well, what if I do this differently and do my sum of torques about over here? Do I end up with the same thing? Well, let's find out. Sum of torques about A. This is also going to be equal to 0 because of statics. We want to make certain that all of our torques end up 0 and all of our forces end up 0. All right, well, I'll have the, let's see, it'll look a lot like this guy, except a little bit different. We'll have the force of tension in A times 0 meters, which is its lever arm. In this case, now that our pivot point is here, tension in B is going to try and make this swing counterclockwise, which makes it positive. Force of tension B times 1 meter. I'm starting to run out of room here, but it's going to look very similar. In this case, our weights are actually going to try and make it swing clockwise. I'm going to write this underneath so that we can see, but so those will be minus. That'll be capital mg times, again, 0.5 meters, acting at the center of the board. And in this case, we're going to have minus little mg times 0.75 meters. Because it's not 25 centimeters from this pivot point, it's actually 75 centimeters, right? Okay, so when I put that in, I find that 0 equals, let's see, my force of tension in the B, because this guy went to 0, because that's where our new pivot point is, times 1 meter, minus, let's see, 2.4525 Newton meters, also minus 11.772, oh no, I'm sorry, I'm looking at the wrong line item, I apologize, minus 8.829, which is going to be our mass of our knick-knack, 1.2 kilograms, times gravity, the acceleration due to gravity, I should say, which is 9.81 meters per second squared, times 0.75 meters, 75 centimeters, because that's how far it is from our pivot point. Okay? And so when I add these up, I find out, solving it fully, that my force of tension in the B comes up to 11.3 newtons. So you can see we ended up finding the exact same thing. Like I said, it's something that seems a little strange when you first start to think about it, but the way the mathematics works out, for something to not move, the sum of torques must equal 0 around all points. We could choose whatever point we wanted, including ones miles away or even ones on the moon, although that would make the mathematics a lot more complicated. In this case, when you go about solving one of these problems, it's convenient to start off with your sum of torques and choose a place that you can eliminate one of your unknowns so that you can solve for the other one. And once you have that, you should be able to solve for the others. Now, one of the things that you could have done, particularly in this case, is found out the tension here by just doing what we did here. Do your sum of torques again from the other point and find out what it is. But at some point when you're doing statics, make certain that you've checked that all of your torques come up to 0 and also all of your forces come up to 0, or else you might find that you've run into a problem. Now, the main place that that will actually come up that's a bit more complicated than what we've dealt with here is with torques using the sine of the angle. There are actually some things that we can misplace if we don't have all nice, neat 90-degree angles. And that's why it's important to go through and double check your sum of forces. Because right now, we could have completely misplaced some forces in the x direction, and that could throw off our calculations. Okay? So, this is one of our sample problems.